going way, way back, right, talked about what we've been doing has been locating the position of a score in a distribution, right? But when we're running our tests, oftentimes not interested in finding a score, right? We're interested in knowing where the mean value of our data fall relative to some reference point, right? And so we talked about how we can take these same principles and start finding the probability of obtaining a sample of our size with a given mean within a distribution of all possible sample means that could be drawn given a certain sample size. Talked about this as a distribution of sample means, right? We talked about central limit theorem, right? So for any population with a mean of whatever that mean is and a standard deviation of whatever the population standard deviation is, distribution of sample means, right? For sample size n is going to have a mean that's equal to the population mean and a standard deviation that's equal to the population standard deviation divided by the square root of n. And this is going to approach a normal distribution as our sample sizes get larger and larger and larger, right? So again, if we think about in terms of, people have sports fans in here? Who's sports fans? A couple sports fans, all right? You think about a team playing a 7-game series, right? The idea of the 7-game series is to determine who's the better team, right? So just so that we don't get one game that's a fluke that throws things off, right? So we have 7-game series. If these two teams were to play 7-game series again and again and again and again and again and again and again, and we took the average number of games that people that these a given team won over the 7-game series, we would eventually end up with a distribution of those means, right? So sometimes our team is going to get an average of 3. Sometimes it's going to get an average of 4, and again maybe another 3, maybe a 1, maybe a 7, right? Every time we go through and have these teams play this series, we're going to get a different number. But if we do this again and again and again and again, holding everything else constant, right? Eventually, the most out of the most trials is going to be our true value of the number of games scored for this team, right? And so maybe, unfortunately, this mean value for our team against this opponent of all possible series is 2, right? Which in a 7-game series is bad news for us, right? But we're not always going to win 2. Sometimes we're going to win all 7, right? It's just that's going to be in the far end of the distribution out here, right? And this is the idea behind the distribution of sample means. Take this example to anything else, politics, any other thing, right? If we're looking at the proportion of the population that's voting for one candidate versus another, right? On one trial, it's a pretty large sample, so it's going to be pretty close, right? But we're going to get variations if we were to hold the sample today, the next day, the next day, the next day, holding everything else constant, right? And this is the idea behind our distribution of sample means. Now, for the types of things that we do, right, thinking about our study as being, and our mean value that we find as just being one out of a potentially infinite number of possible means that could be found given a sample size, whatever sample size is, right? And what we find is that even with data that are non-normal, right? Even with data that are pretty skewed out there in the population, think about aggression in children, that tends to be a skewed distribution. The distribution of sample means will still be normal under 2 conditions. One, when the population from which samples is drawn is normal. So talking about height, weight, intelligence, things like that, different types of personality that work on a normal distribution. Sampling distribution of means is probably going to be normal very quickly, or if we have reasonable sample sizes. Now take this 30 as a grain of salt. Statistically, that's where we start to see a break in sort of the addition, the benefits we get to decreasing our standard error starts to drop down once we get to about 30. 30 is not a large sample, 30 is a small sample. It's a nice cell size if you're running an experimental ANOVA approach, right? But if we have samples that are around this point or more, we find that the distribution of sample means starts to approach normality pretty quickly, and this starts to become important when we start talking about our assumptions of our t-test, okay? We talked about how the expected value of the sampling distribution of sample means, our expected value of m, is going to be the mean of our sample means. The mean of our distribution of sample means is equal to what, Sam? Mathematically, what does the mean of our distribution of sample means represent? Okay, that's technically, yes, you're absolutely correct. That is what it means. Conceptually, mathematically, what does it represent? The population mean. The population mean, right? And so if we take the average of all possible means that we could get, the average of that means the expected value of the mean is equal to the population mean. This starts to become important from a mathematical standpoint. This is what all of our statistics are based on, right? So we talked about central tendency, and then we talked about variability of our distribution of sampling means, right? What is the variability in our distribution of sampling means, Stephanie?
You asked what? What is?
I said, what is our measure of variability for the distribution of sample means? Okay, what type of error?
I don't know. Does anyone help me out?
Standard error, right? When in doubt, yes, standard error. It's probably right. Standard error is just, like, literally it is the standard deviation of our distribution of sample means. From our hypothetical distribution of sample means, standard error is just the variability that we get in our sample means. But conceptually, what we interpret this, our standard error, we can interpret it in a couple of different ways. So literally, if I asked you what the standard error is, and you said the standard deviation of the distribution of sample means, you would be correct, right? Conceptually, what this represents is an index of how much difference is expected from one sample to the next. I was just doing this the other day. So I'm running a project. I've gathered several large samples in the range of 350 to 500 to 600 people, and was calculating the mean for for the value of the measure, right? And so these are really big samples, and I went through and I was just curious because I had 3 samples, calculated my standard error, right? So for standard error, took my standard deviation divided by the sample size and got a value of about 2, right? And then I went through and I looked at how much across these different replications, same measure, same population, big sample sizes, how much would you expect that I would see that the mean of each one of those samples to jump around by? If my sampling error, or if my standard error was 2. So what do you think, Katie? 2 points, right? About 2 points, and it was really fantastic because across these 3 samples, they differed by a maximum of about 2 points, right? Which is what we would expect based on the calculation of our distribution of sampling means here. Our standard error is telling us if I were to do this again with the same sample, on average, how much would I expect my replication sample to deviate from the sample that I've got? And if I were to do that again and again and again and again, on average, how much would I expect this to jump around? Now, does that say it can only deviate by 2 points? No. Would it be weird if it deviated by 4 points? What do you think? Would that be an odd outcome, Rajiv? If my standard error is 2 and I got a sample that was 4 points different than another mean, is that weird?
No.
Why not?
Because whenever you replicate or take a lot of samples, some sample might be outlier, or there might be.
Mm-hmm. And is 4 even an outlier in this situation?
Not really.
No, it's just 2 standard deviations, right? I've just got a sample that's within a couple standard deviations of my last sample, which is still not way out of bounds, right? Now, if I get a sample that's 10 points higher, boy, that's 5 standard deviations. That's pretty, that's out there. It's not impossible, but it's very unlikely, right? And so thinking about your standard error is how much difference would we expect from one replication sample to the next. Also thinking about this is how well any individual sample is going to estimate the mean of the population. Right? If I've got 100 people in my sample, right, and I get a standard error estimate of 2, and I'm gauging things on a 0 to 100 scale, how precise is that estimate? What do we think? So my standard error is 2, and scaling on this can be 0 to 100.
And you're asking how precise that
Yeah,
is?
yeah.
Pretty precise.
Pretty precise, right? What that's saying is, on average, I'm expecting my mean across replications to jump around, or on average, how far my sample mean is going to be from the actual population sample mean. On a 0 to 100 scale, if I'm 2 points away, I'm pretty happy with that. That's pretty good, right? And so this starts to be when we start thinking critically about these as not just numbers that we're creating, but actually concrete, like what they actually represent, starting to get a sense for how good is my sample. I have a sample. I like my sample because I collected it, and it represents, it's a part of me, this sample is. But how good of a sample this actually is in terms of getting near or close to the population parameter that I'm actually interested in, starting to think about standard error in terms of judging some of that, okay? And then we can also think about standard errors, expected difference between the sample mean and population mean, right? So between 2 randomly selected, average distance between 2 randomly selected samples, average distance from the any randomly selected sample from the population mean, right? So again, wanting you to internalize this idea of standard error as a real thing and not just something that you're forced to calculate to get p-values. Okay. Questions about standard error? You want to know standard error is involved in everything we'll ever do, always. So I want you to make sure you've got a sense of that. Okay. Factors influencing standard error, and this is where being comfortable and not avoiding your gaze from formulas is helpful, because if I ask you what things influence standard error, and that's the equation, what are the 2 things that can possibly influence standard error? Yeah, sample size and standard deviation. This gives you the answer right there, right? And so thinking about, as my standard deviation, as the variability in my sample gets larger, we'll system out all things else held equal, will increase my standard error. But the big thing here is your sample size. As our sample size is increased, that just drives down your standard error. Morgan, why is this?
Sample size increases?
Yeah.
But the denominator is getting smaller.
Perfect. Okay, so mathematically, from a ratio standpoint, conceptually, why is our standard error getting smaller as our sample size increases?
Because we are including like the outliers and the broader representation of the population.
We're just getting a better representation, right? We've gotten a larger sample. We're more likely to collect those people out in the margins, and we're getting all the people there towards the middle. All things being held equal, we're just getting a more stable estimate of our population parameter, okay? So we talked about our 3 different samples. We have population of scores, right, that are, for many of our constructs, is going to be relatively normal in shape, which is nice. But when we sample scores from that population, we may get something that looks decidedly not random, or not normal, particularly when we have not very large samples. You'll see this as we start screening data. When we get work with very large samples, things tend to look kind of nice. When we get into small samples, things look kind of busted and choppy, right? But even when our samples are busted and choppy, our distribution of sample means, again, from a theoretical standpoint, we would expect to reach normality very quickly based on if we're measuring something that has itself a normal distribution, or as our sample sizes reach reasonable number of people in them. Okay. So this all ends up being important because what we can do with this based on, based on the property's distribution of sample means, what we can do is we can start assigning probability values to the likelihood of obtaining a sample of this mean or higher based on the assumption of some sort of reference point. And we do this by calculating our z-score, same thing as we did previously with identifying the position and probability of scores. This time we're just identifying the position probability of means. Our z-score here is going to be our mean value that we get from our sample. We're going to subtract this from a known population mean and divide this by the standard error of the sample distribution. Okay? I need to practice somewhere else. Okay, so with the types of things we can start to answer with this, SAT scores form a normal distribution. What's the probability of selecting a random sample of 10 students? SAT less than 440. Talked about, I don't know, so they're 4/10 of a standard deviation below the mean. That's probably not terribly unlikely, right? Particularly with only 10 students. As soon as we start to get 75 students, that starts to become less and less likely, right? Identifying middle range of likely samples, things along those lines. So, and this is going to be important too. I want you guys to really make sure that you have a good handle on this. Anytime we see patterns of data, two different explanations, and it's really hard to tease apart which one of these things we've got. One, so we got some systematic factor causing X and Y to be related, or group A and group B to be different than one another. So we've got a real effect, or this is just chance fluctuations, right? Our inferential statistics is what we do to try and tease some of this stuff apart, right? Trying to determine, is this difference that we're seeing real? Is this difference that we're seeing represent differences in population values? Or is this just basically sampling error, stuff that we would expect across numerous different replications? Okay. So again, we had talked about this example. We've got some known population value. We've got a population with a known mass here. And then we take members of that population, we do something to them. We expose them to a treatment. Are they still part of this population? Nope. They're part of a different population. They're a new population that's been exposed to this thing, right? These are the rats that have had X handed to them. This is a new population. We don't know about this population. What we're interested in is determining whether or not the characteristics of this population are different than the characteristics of this known population. Now, we only have, say our sample of 10 treated rats is all known. This is all the 10 rats that are there in the world, right? Because these are the only 10 rats that have received this treatment. But from a theoretical standpoint, these 10 rats represent a population, a hypothetical population of all possible rats that could receive this treatment, right? And we know that this is just a sample of all possible rats that could receive this treatment. So what we want to know, if we see that this sample of treated rats has an incrementally higher mass than the population mean of these rats, because they've been bred to be all identical, right? They're all clones. What we need to do is have some way of teasing apart whether or not the hypothetical mean of this population is systematically different than this known existing mean. Okay, and this is where our hypotheses tests start to come into play. So, transitioning from rats into humans, and we've jacked up on stuff. We're working with this example. We believe that antioxidant supplements could reduce age-related cognitive decline, right? So we think that supplements are going to be helpful. We take 25 adults, older adults, have them take these supplements for a period of 6 months. So who does this sample now represent? What do you think, Alex? Okay, So we've got 25 older adults that we've fed supplements for 6 months. What's the population that these individuals represent? Older adults. Okay. So they are older adults, right? But are they now representative of the larger population of older adults? Shaking your head, no. Because who do these people now represent? We've transformed them into a whole separate population that represents who? What's that? One more time for the camera?
Taking the supplements.
Yeah, the population of people, right? So they represent a hypothetical population of individuals who systematically take these supplements that we've given them, right? And so what we want to know is whether or not this new population is systematically different in parameters than this existing population that we already know about. Right? And so this is a little bit tricky, but wanting to think about this when we're doing research, right? There's a couple different types of if we're doing individual difference types of research, right? We're saying, is this group different than that group, right? These two populations are already an existing population. They're people out in the universe, right? And so we say, are men taller than women, right? Are this better than that, right? Or something along those lines, right? Those are existing populations. But when we start to get into experimental types of things, right? If we bring people in and expose them to experimental manipulations or different types of treatment, what we've done is we've now created a hypothetical population that these individuals represent, and it's the hypothetical group of all possible individuals that could receive this treatment, this manipulation, things along those lines. So Sam, if you bring people in and you expose them to different jury instructions than are typically given to jurors, right? We've switched this up. Right now, there is no population of individuals who's received these jury instructions because just the people in my experiment, those are the only people that have heard of them, right? These people are representative of the population. If we were to provide these instructions to all juries, this is the representation there, right? Same type of thing if you're doing treatment outcome study, right? You've got a new treatment that no one's ever had before, and you've got 20 people that you give this treatment to, right? These people who receive this treatment are no longer representative of the population of individuals with depression, but the population of individuals with depression who have received this treatment, right? And what we want to see is whether or not the expected parameters of that hypothetical population are different than some normal reference value. When we're using our z-test, it's some known population parameters. Okay? So for this test, we now have a population of older adults. So our point estimate for the mean cognitive score for the population of older adults taking supplements is, I guess we're not giving them, but that's who they're representing, right? And what we want to do is we want to compare the parameters that we get, our estimates based on our sample, against the known population score on this cognitive test for individuals 65 and older has a mean of 80, standard deviation of 20. So people see kind of what we're doing and the setup for this. Yeah.
So in this scenario, can't the population be the individual who takes supplements, those who are 65 and above the age?
I'm sorry, one more time.
So the population that we were talking previously, couldn't this be like the individual who are taking the supplement and those who are like 65 and above age?
Right. So everybody's 65 and older, right? So we have older adults. Everybody's older adults. But what we're going to do is we're going to say, is the population of older adults who are taking supplements, that hypothetical population, is the mean cognitive functioning for that population different than the reference group, which is going to be just all older adults.
And the older adults means like the age from 65 and above.
Yeah.
Okay, so we don't have to define.
No. But I do want, as we're going through and talking about, and as you're writing this up, I want you to I want you to tell me that's who we're talking about, right? Not just adults. We're talking about this specific population. The specific population we're working with is older individuals, right? And so wanting you to tell me that, because if you don't tell me that, I don't know that you recognize that. So I'm gonna take you at your word. I'm gonna take you at face value. If you tell me something, I'm gonna assume that's what you mean, because it's hard to say, well, you know what I mean, if we're talking about science, right? So make sure to go through and be inclusive as you go. And I'll give you some examples of some write-ups and things like that a little bit on the slide. Yes, Sam?
So with hypothesis testing, you're trying to see if that population actually exists?
No. I'm not shouting no at you, but I see where you're getting. Right? I guess technically I did shout no at you, but that doesn't mean, I think it's an excellent question. No, it's, so the point of the hypothesis test isn't to test whether or not this population exists. The population exists, right, by definition, and because of the fact that we did them. They're distinctly a different population than the population of older adults because we've had them do this one thing, right? The question is whether or not the mean value of cognition in this population is different than this population, right? So it's a different population. We can split people into all sorts of different populations, right? I want to look at the population of men over 6 foot tall with blue eyes with no hair. And it's a population, right? I don't know if it's meaningful or different than any other population, right? But what we're doing, we're saying, yeah, this is a different population. We just want to see if the distribution of characteristics of this population are systematically different than some known entity. Okay, does that help? Okay, cool. So for this process, what we're going to do is we're going to state our hypotheses, right? And hopefully our hypotheses are always made before we collect the data and not after we see the data, because then it's not the hypotheses so much, and there's complications there. We're going to set the probability to determine our reliable effect, collect our data, calculate our statistics, and then draw some conclusions. Okay. Step one, stating the hypotheses. People probably familiar with this whole process, working with two related hypotheses. Our null hypothesis says that there's nothing going on, right? Our null hypothesis is saying there's zero relationship between our IV and our DV, X and Y are unrelated, the treatment has no impact on the outcome, all sorts of different ways we can talk about this, right? Our alternative hypothesis says that there is a relation between the IV and the DV. Treatment has an effect on the outcome. Population A is different than population B. Things we want to do, though, when we're stating our hypotheses, remember always, always, always that we're talking about populations here and not about the samples. We don't care about the samples. We only care about the samples insofar as they are represented, our representation of the population. I don't need to do a t-test to see whether or not the mean of sample 1 and the mean of sample 2 are different, because I can just look at them, and if the numbers aren't the same, they're different, right? But what I want to know is whether or not the differences that I'm seeing in these samples represent, if I can infer a systematic difference in the populations from which they're coming from. And so when you're talking about and writing out your hypotheses, always wanting you to make sure that you're telling Candace and myself that you recognize that this is a hypothesis about differences in population values, and that you know what population we're talking about, right? This is just going to help you make stronger interpretations once you get everything put together, okay? Now, our null hypothesis test, only designed to test the null hypothesis, and we're going to get into the limitations of this at the end of the lecture. But based on the evidence of the sample, we're either going to reject the null hypothesis or fail to reject the null hypothesis. Null hypothesis is the only thing we're focused on here. So for our supplement example, our null hypothesis is, we can state these in a couple ways. Here's statistical notation, how we might state this, right? If we were to say this in words, our null hypothesis might be the population of older adults using herbal supplements is equal to 80. Right? Our alternative hypothesis, population of older adults using herbal supplements is not equal to 80. Right? So you can see in these statements what we're doing is you're identifying what the population is, and you are actually, I need to go back through. Candace, can you shoot me an email and tell me to fix these? What might I not like about these two population statements?
Is age referred to?
Exactly. Nice. Gold star for you, Morgan. I don't know what the hell 80 means, right? Who knows, right? And so wanting to go through and probably what I should say is say something along the lines of the population of older individuals using herbal supplements will have a mean memory score equal to 80 or something like that, right? Or we expect an average memory score of 80 in the population of older adults using herbal supplements. However you want to say it, right? But want to get in and make sure we know what 80 means. Again, this is going to force you to start thinking about your units, and it's just going to enhance your interpretations of things we talked about. Okay. So once we do that, we set up our hypotheses, and then we're going to set our decision criteria. Actually, you won't, because it's set for you based on our field that we work in. But from a theoretical, sort of a systematic standpoint, this is really up to you, right? What we want to do is we want to determine how often we're just going to find things that are aberrant and how far are we going to set our benchmarks out here. What we want to do is set the probability of obtaining the sample, assuming the null hypothesis is true, that's at a level that we're going to start to say, okay, we can start making inferences about this. If we find that our sample means much different than a proposed population mean, right? We're going to determine this is incompatible with either the null hypotheses or the assumptions of the statistical model. Important thing, and I think Howell talks about this, a couple other people, is that we don't know which, right? So we find, assuming a population mean of this, we find a population mean that's out here based on our data. And we would say that these data are, assuming that this is the null hypothesis, or assuming that the population value is this, it would be very unlikely that we would find, get a result at this level or higher, right? But what we don't know is whether or not that's a function of our null hypothesis or whether or not we've violated a bunch of assumptions either knowingly or unknowingly that have led us to obtain a wonky estimate, okay? Now, we're going to go through and systematically make sure that we can screen for and know all the knowable wonky things that have gone on. And we're going to use our good brains to think about methodologically if we've done anything that's wonky or weird, to try and increase our confidence that, yes, we've met all the assumptions of our statistical test. Our methods aren't perfect, but they're probably reasonable enough. And so the likelihood of obtaining a sample at this level or higher is probably low, assuming that this is our null hypothesis. Okay? But these are the types of things, if you're doing this at a professional level, you're all doctoral candidates, so I expect you to all do this at a professional level. These are the types of things you want to be aware of and be thinking about. Okay? If, however, we go through and find our sample mean similar to the hypothesized mean, we interpret this as relatively compatible with our expected value under the null. Our null hypothesis tells us whether data are unusual given the null hypothesis, but it doesn't imply that the model or any aspect of it is correct. What are we talking about here? What do you think, Angela? What am I talking about here, and why is this important? What's that?
Null hypothesis testing will tell you whether, like, your data in the sample is different, like whether it differs from the population.
It can tell us whether or not it's unlikely, right? Assuming the null hypothesis, we can say these data are likely, but we can't say with certainty that that the mean of this population is 100% certain different, right? What about this piece that we can't apply that the model or any aspect of it is correct? You want to jump in there, Sam? Yeah.
Is it that we didn't violate the assumption?
Okay,
and
so,
do good stuff.
but even if we didn't violate any assumptions, why can't, how about this? How about this? What would be problematic if I ran a test and I rejected the null hypotheses and I said that these data prove that my theory is true? Okay, yeah.
Or
And so what else could it be due to? Okay. Angela, my theory is that space aliens make men taller than women. Okay. Space aliens are constantly raining down things to make us men taller than women. Okay. And so I go and I collect data, and I find that in fact men are taller than women. Hypothesis confirmed. Space aliens causing differences. Right. What's wrong with that logic?
that's causing.
What's that?
You just don't know that that's causing.
Well, so if we want to get into some of the causal issues, what's maybe the bigger problem with that scenario?
Aliens aren't real. You
What,
can
right,
test anything with aliens.
my theory's nonsense, right?
Yeah.
My theory, I can't just say things, right, and then test the data. Like, my theory just happens to be making predictions in the same direction as biology,
Yeah.
right? And so my null hypothesis test says nothing that say anything about the truth of my theory or whether any of the mechanisms in there are true. At best, I can say that these data, results from these data, are consistent with my theory, consistent with predictions made based on my theory. They do absolutely not provide a test of the actual fact, the reality of your model, right? But this starts, and we'll talk about this in a moment, where people start to, well, I found evidence that's consistent with my hypotheses, therefore my model is true. Okay. The first part of it, fine, you can say that. Second part of it, way out of bounds. Yeah.
But don't we kind of figure that out through our manipulation? Like if I change something or something.
Okay, but that's a methodological issue, right? That's the process of building evidence for your theory, right? But your hypothesis test doesn't do any of that. All your hypothesis says is assuming this null value, these data are either likely or unlikely. Okay, so the process of research and scientific method is an approach by which you can start to gain evidence in support of a theory as a whole, right? But your one hypothesis test never tells you anything about whether or not your theory is true or not. It just says, given this assumption, these data are either likely or unlikely, right? And that could be because one, the specified null is not a reasonable estimate, or based on our the population parameter, based on our estimates, or two, I just made a bunch of gross violations and I don't know what I'm doing with my statistics. Okay. Be ready to be incredibly disappointed with our whole system of science by the end of this lecture. I'm just gonna grind you all into the ground with this. Okay. But we'll get that back to sort of this topic here. But in terms of setting our decision criterion, our threshold for statistical significance determined by you all, given as your alpha level, probability threshold used to find your critical regions. Okay, this is where we're going to set our markers for saying if we get data that extends out beyond these values, we're going to say that these are data that are unlikely under the null hypothesis. Okay. But because we work in a science where we kind of try and play by the same rules, you don't really get to set your significance value. What's our significance value usually set to? 0.05, right? That's just our standard that we've accepted as sort of our threshold, for better or for worse, right? But we can go through and set out thresholds that are more stringent. You're going to get in trouble if you try and set thresholds that are less stringent. Although there are circumstances where that might be reasonable, you may be able to mount a defensible argument for saying this is, I'm gonna set my alpha level at alpha 0.10 or something along those lines. But it's gonna be a hard thing to do, okay? So these are our benchmarks, right? And we're saying that any data falling in either one of these tails is gonna be unexpected, assuming that the null is true. So we've set our goalposts, okay? And what we're now going to do, most basic scenario, calculate our sample statistics based on our known population parameters. Remember here when we're using z-tests, we're assuming that we have access to actual population parameters involving mean and standard deviation. Okay? What types of situations might this be true? Under what circumstances might we know a population mean, population standard deviation? Okay, so right, if we're testing things right where we have a standardized measure where we know the population parameter, if we're comparing this group of individuals who had a cognitive enhancer against known parameters on this test, that might be a situation. Okay, what other examples might we have access to population mean standard deviations? What's that? SAT scores, okay. So again, something where we're working with a standardized normed measure. Biology, right? If we have biological samples where we know sort of what the parameters are, or in other hard sciences, physics or something like that, we know that this is the population, is like this is the thing, right? These are situations where we may be able to compare a sample statistic that we've collected with some known population parameter. If this is the scenario we're in, we can calculate our confidence intervals by taking our mean sample value from our new population that we've sampled from, plus or minus z critical times our standard error. Z statistic, our test statistic, calculated so that we can determine the location probability of this sample mean relative to the known population parameters, okay? So here with our z-test, we're taking our sample mean, subtracting a reference value, all right? And that reference value being the known population mean, taking that by the standard error of the mean. Standard error is calculated as the population standard deviation divided by the square root of our sample size. So if we look at this and start thinking about this critically, we can see that the numerator of our test statistic is the difference between their sample data and our assumed population value, right? This is just a deviance score. This is just a discrepancy, right? This is telling us literally how far our mean, the mean of our sample is from what we would expect under the null hypothesis, right? This gives us how much difference we see. The denominator, this is the expected difference between the sample mean and population mean under the null hypothesis. Okay? Why is this what? How did I get this this interpretation from the denominator here? What is the denominator? Standard error. Right, I told you that was a good guess on everything. It's a standard error. And Angelina, what is the standard error? What's our conceptual interpretation of the standard error?
The sample differs or like varies from the population.
Exactly, right? And so, the numerator, if we think about this, the numerator is how much difference we've seen, right? The denominator is how much different we would expect just based on random sampling error, right? And if we see a lot more difference than what we would expect based on expected deviations, what's our set test statistic going to do? Or in your Queen ratios, is it going to be high or low?
Sorry.
If if we're seeing a lot more difference than we would expect based on just the sampling error, we're going to have a large test statistic or a small test statistic.
I'm sorry, I don't know my brain's being
Okay, so if we're seeing a lot more difference,
Yeah.
right? So here's where I think where my expected population mean is. Here's where I'm at. We've got a big difference here.
Yeah.
I got a lot of difference here, and it far exceeds the difference I would expect just due to random sampling variation. Is my test statistic being large or small? It's going to be large, right? My numerator is going to be big, my denominator is going to be small. What happens if I end up with a difference that ends up being about what I would expect based on just random sampling error? It's going to be small, right? Or about 1, right? I'm getting about as much difference as I would expect based on what I'm going to get variation in terms of my sampling this thing over and over again, right? And then I'm going to get a test statistic that's small or close to 1, right? And so you can look and see the logic behind this test statistic, right? It's not a magical thing that's been documented by wizards and tables, right? It actually reflects true, actual, sort of meaningful stuff if we're taking a look at it. And this is the type of thing it's important to understand and recognize and be able to interpret so you can catch yourself if you start getting crazy answers to stuff. It may be exciting when your T statistic of 35 pops out, but you want to make sure that you go through and check that to make sure that that actually is a meaningful thing. Okay? Yeah.
So the difference that is expected, that's the numerator, and then the actual difference is the denominator? Or is it
Okay.
the other way around?
Other way around, right? So up here, this is just what we've seen, what we've observed, right? Numerator is what we've observed. Denominator just tells us if this is something that we would expect, assuming that the null hypothesis is true, right? Assuming this, we would expect across an infinite number of replications on average, our samples to differ from the mean by about 3 points. If I found 18 points difference between my mean and the proposed sample or population mean, and I only expect 3 points difference based on my standard error, I'm going to get a big test statistic, right? It suggests that these data are unlikely. Obtaining these data is unlikely, assuming a certain parameter for the population. Okay. So we're going to do a couple of examples here, using our Ginkgo things, right? So what we want to do is calculate Z statistic. If an individual taking antioxidant supplements with a sample size of 25, scoring an average of 92 points on the neurological assessment, right? So that cognitive assessment that we know has a mean among older adults in the population has a mean score of 80 and a standard deviation in the population of 20. We run a sample, we have older adults, we have them take these herbal supplements for a period of 6 months, we give them this assessment, and we find that they have a mean score of 92, right? So, N25, our mean for our supplements is going to be 92, right? What's the first thing we need to do? Standard error. See, look at that. You guys are catching on. I told you that. So just shout standard error at me anytime I can. All right. So standard error is going to be, so mean under the null is 80. Standard deviation of the population is 20, right? Standard error is going to be 20 over the square root of 25, right? So we're taking the population standard deviation divided by the square root of my sample size here. Gives me a value of 4.0. Katie, can you give me an interpretation of that standard error? What does that mean?
That we're expecting about 4 points.
Absolutely right. 4 point what? on average, right, if we were to take population of individuals at samples of 25 and just measure their average score on this cognitive test, we would expect on average any two randomly selected samples to be different by about 4 points, right? We would expect any randomly selected sample to be about 4 points away from the mean on average. Could be more, could be less, right? But on average, this is our standard areas telling us how much we're expecting things to jump around, right? What do we want to do next? Okay? What do I want you to do next? I should calculate a confidence interval. Okay. So our 95% confidence interval is going to be our mean value, 92, plus or minus 1.96. Rajiv, where did I get 1.96?
From the Z to 95%.
95% times what? Standard error, right? 1.9, which will give me confidence interval 84.16, 99.84. Okay. Oh, who do I want to pick on? Yeah, like 0 people looking at me as soon as I say that, right? Angela, can you give me an interpretation, conceptual interpretation of that confidence interval?
So given our data, we were just choose a random, it's likely to, it's probable that it'll fall between 84, 16, 99.
Okay, so getting there, picking up some of this stuff, right? Remember, wanting to make sure, and this is easier to do if you're sitting down and like writing things out, right? Wanting to make sure you're capturing, providing a good conceptual interpretation of the thing, make sure we're identifying things as a population parameter, right? I might say with this that based on my data, the range of plausible values, the average score on this cognitive test, the population of individuals taking these supplements, ranging anywhere from about 84 to close to 100 points, right? Or I might say, based on these data, we find a reasonable lower bound estimate for cognitive score on this test in a population of older adults taking supplements, about 84.2 with an upper limit of 99.8. Okay. We can talk about things in terms of margin of error. Margin of error is 1.96, 2 times it's close to 8, right? Now, knowing what we know about cognitive tests, is 8 points a lot or a little to be jumping around on a cognitive test? Do I have a precise estimate or a not precise estimate? Not super precise, right? I mean, my margin of error here is about close to 8 points, which is almost half a standard deviation. I'm jumping around on stuff, right? So I'm not super excited about my interval because it's pretty wide. Why is my interval wide? What's that?
Your population for deviations.
Okay, not my population is low. What is small? My sample. Okay, sample's small, right? I mean, 25 is not a big sample, right? So we're not super precise, right? So we've got some variability around this. So these are the types of things we might want to think about, okay? Now, if my question is, and the whole reason I'm doing this is to make a determination on whether or not herbal supplements are a useful thing and help improve cognitive functioning, Rajiv, what might be my conclusion based on my confidence interval?
What is the confidence interval? I can't see anything, so.
Oh, I'm sorry. It's confidence interval 84.1 to 99.8. Right, 84.2 to 99.8.
So based upon the confidence interval, you can see that it has some effect on the older population who takes the supplement.
Why is that? Why are you saying that?
Due to the margin of error,
Uh-huh.
it's not like, so the standard deviation, I don't know how to say this, but
What's the big, and I think you're right, Based on these data, we could reasonably conclude that supplements are having an impact on cognitive functioning in the positive direction, right? What's the main thing that gives us confidence in making that interpretation based on these data? Anybody have an idea? Katie? Yeah.
Population parameter for individuals not taking the supplement doesn't fall within their.
Exactly, right? Our population, so this is, there's no variability in this, right? We don't need to create a confidence interval around that because this is the number that it is, right? But we find that even though we've got some fuzz around this with a sample of 25, 80 is not within this, right? So we're saying, right, if we take a look at this, 80 is not plausible, but based on the data that we've collected, 80 is not a reasonable estimate for the true population or the average score of this cognitive test in the population of individuals taking supplements, right? It's not in there, and so it's not reasonable, right? I mean, it's not impossible, but just based on these data, it looks like a score of 80 as the mean value for cognitive functioning or cognitive test in this population of individuals taking supplements is not reasonable, right? So we would identify the population value as relatively implausible based on the data that we've collected. Okay. People see where we're getting that? So at this point, what we can do is now we can go through, calculate our Z statistic, right? And our Z statistic is going to be 92, our sample mean, minus our reference mean, over our standard error is 4. It's going to give us a value of 3.0. And is that going to be statistically significant given alpha equal 0.05? A Z-score of 3? Yeah, what does that say? Yeah, it's around 99%, right? And my cut point, if I'm going through and running my hypothesis test, right, I'm calculating this. My cut score is 1.96, or about 2, right? I'm at 3. So am I going to reject the null hypotheses? Yep, I am, right? But you can start to see, okay, did I even need to do my Z test after I'd gotten my confidence interval? No, right? Only thing that my Z test gave me is a p-value, right? But if I'm looking at that, if I can say a Z-score of 3 and a p-score and a p-value of whatever that is, 0.001-ish, not quite there, that would be 3.29, but versus this, which one gives you more information? Confidence interval, right? But you'll notice that both of these things are all based on the same information, right? There's no new information that's going on here or here, and so what I don't want you to say in your interpretation is that we reject the null hypotheses. Here's the p-value. I ran a confidence interval, and my confidence interval confirms that we should reject the null hypothesis. Your confidence interval doesn't confirm that. It's just repackaging the same information in arguably a more useful way. Okay. Questions on this? Yeah.
Are we going to go over like how confidence
Oh, it's all based on the same stuff. It's the same. We're using the same values Same thing with our T-scores and things like that. So it's all the same information, or it's all using the same pieces and parts. It's just here, we get a point estimate, an estimate of the precision of that point estimate, and giving ourselves values so that, say, if the next person goes through and tries to run a replication of our study, right, or runs this in middle-aged adults or things like that, you can say, well, based on this interval, it looks like our values are kind of in the same range. So here, let's go through, run a different scenario. But this time, instead of mean supplement value, we're going to say it's 84. Is that right? So scenario 2, right? So again, our standard error is still 4.0, right? Because none of that stuff changed at all. So our 95% confidence interval is going to be 84 plus or minus 1.96 times 4. That's going to give us 76.16, 91.84. Okay. And then if we run a Z, it's going to be 84 minus 80 over 4. Just 1.0. What about Stephanie? What is our? Give me an interpretation of our confidence interval here.
Given just a moment, so I can make it work. Given our data, it is likely that the population mean falls between 76.16 and 91.84.
Perfect. Except for what? What did Stephanie forget? Okay, so one, we want to know what population you're talking about, right? And
Oh.
two, we want to know what means we're talking about, right? But that's to get that into something that makes sense in terms of English and communicates that effectively, that's something you'll get down with practice, but always remember that we want to work with data. And so we might say, based on the data that we've collected, 95% confidence interval suggests that plausible values for mean cognitive score in a population of older adults taking herbal supplements, somewhere between 76.2 and 91.8, right? Alex, based on that confidence interval, what might we infer about the impact of taking herbal supplements?
The population is
Okay. And so what does that, and so conceptually, how would we interpret that?
that means supplements is beneficial to the population.
Do we have any confidence that it's beneficial? It might be beneficial to the population. We just don't know, right? Because we were going to reject the null hypothesis, and we see that with our z-score of 1, right? That doesn't fall within our critical range. At best, we throw up our hands and we say, I don't know, right? Maybe it does, maybe it doesn't. We just don't have sufficient evidence based on these data to make the claim that there's a reliable impact of supplement use on cognitive functioning in older adults, right? Now, Sam, like you were saying, we still have this, we're still working with a unique population. This is a population of individuals, older adults who are taking supplements, right? So it's still a population that's separate than the general population. We just don't know that this population has a mean that's any different than the mean in the general population. right? So essentially what we're saying is, this is one population, and this is another population. They're different populations. I just don't know that their average cognitive functioning differs across these two based on the data that we've collected.
So would you put that in your interpretation then?
What's that?
Would you put that in your interpretation?
You should.
I just don't know.
Yeah, I mean, now, as you get out into writing papers and things, and you have less space to be very specific about things, although I would hope that you continue to still incorporate these types of explanations in there, right? Just because it's scientifically correct, and we'll look at how for the past 80 years we've been talking about how the way we talk about things is problematic and why that's problematic, right? But for this class, absolutely, that's the level at which I want you to demonstrate to me that you understand what's going on, making reasonable interpretations, working within a flawed system. Okay. Questions about any of this? Okay, cool. So, scenario one, where we've got a mean, we found a mean of 92. Here are our markers for our z-scores, right? Here's where our test statistic fell. And so we would say this has fallen within our critical region, right? And we would reject the null hypotheses. Scenario two, with a mean of 84. Markers are the same. It's just now here's our test statistic, falls within the body of the distribution. It's higher, right? Absolute value is different. It's 4 points higher. It's just that 4 point difference that we've seen is about the same average difference we would expect across different samples, or between on a randomly selected sample. On average, it's distance from the population parameter, and so we would fail to reject the null hypothesis there. Okay. So then what we do is we draw our conclusion. Meaningful conclusion about the possible population parameters. Want you to take into consideration precision of the estimate, size of the effect, based on confidence interval. We'll talk about that a little bit more maybe later today if we get there, right? But wanting to draw these things together to make a meaningful interpretation about answering the question at hand based on the data that we've got. Okay? A couple options. We can reject our null hypotheses. We're going to reject the null hypotheses when our sample statistic falls within our critical region, right? If our sample statistic is falling with the tails of the assumed distribution, suggest that the sample data are unlikely, assuming the null hypotheses and that all corresponding assumptions of the statistical model are true, right? So again, getting back, so these data are unlikely, assuming that this is, assuming the value under the null hypotheses, and we haven't grossly violated basic assumptions of our statistical test, right? It's like, you got a wrench and you're using it as a hammer and beating on stuff, right? You know, you have to make sure that you're using your tools appropriately. And what we would do is that we would conclude then, based on the rejection of the null hypotheses, that the sample was likely drawn from a population with a mean different than the one specified under the null, right? And we interpret this as indirect support for the alternate hypotheses. So in our first example, right, we're assuming that the sample that we draw, that in the first scenario, we're assuming that sample of 25 older adults taking herbal supplements. We're assuming that we drew that sample from a population having a mean that's different than what we specified under the null hypotheses, right? Our confidence interval tells us the range of values that we expect that mean based on what the mean is based on our data, right? But we're saying that this population now it's always been a different population, but now we're assuming that this population has a different characteristic than than whatever characteristics were assumed under the null hypotheses. Yeah.
So we can't prove anything because we're not actually sure how that population looks. We can only assume.
Exactly. We never prove anything, right? And it's possible that we've made an error, right? Maybe the population of older adults taking herbal supplements maybe it is 80, right? And we just gotta wing that sample way out on the edge, right? There's no way for us to know that based on the data that we have, right? That's information that's outside the box that we don't have that we're not privy to, right? We can say that based on the data we've collected, it suggests, right, that the population of older adults taking supplements has a mean value that's different than 80, specifically greater than 80, right? But we don't prove anything, right? What we would need to do is replicate and maybe do different types of things, right? And that's where our methods start to come into play in garnering support for this hypothesis. But based on one study, it tells us very little. Okay? So we never accept the alternate hypotheses, right? We just reject the null and use that as indirect support for our alternate hypotheses. We never directly test the alternate hypotheses with the standard conventional null hypothesis testing. Failure to reject the null, make this decision when our statistics fall within the body of the distribution, suggests our sample data are plausible under the null hypotheses, right? Not gonna be exact, but based on what we would expect due to sampling error, right? We would expect that these data are not inconsistent with what we would expect to get from if our experimental sample actually did have a mean value in the population that was equal to whatever we had specified under the null. And again, we conclude that there's insufficient evidence to claim an effect. It's an agnostic versus atheist type of approach, right? We're not saying that there is no effect. We're not saying that the effect is zero. We're not claiming support for the null hypotheses. We're just saying that we don't have enough evidence to say that it's not plausible. Okay? Does not prove there is no effect. And so I still get caught up with it. They've gotten called out by reviewers, right? Generally when I'm trying to sort of demonstrate that my two groups aren't systematically different on stuff that I don't want them to be systematically different in, right? If I say, ran tests in chi-squares and we found no difference across these two. Well, not no difference because they're different values. All I can say is that I don't have evidence to suggest that there's a systematic difference across my experimental and my control group based on the data that we've collected. But it absolutely doesn't say that they're the same, right? And this people say ran a test, and we rejected the null hypotheses, and which means these groups are the same. Oftentimes, these groups are 9 and 10, right? I'm not shocked that you didn't find a significant result, right? That tells you nothing aside from probably you just don't have enough power to detect the differences in these two groups. Okay? Never use the unfortunate phrase, accept the null hypotheses, right? We don't accept the null hypotheses. We just reject or fail to reject, and if we fail to reject, best thing we can say is, I don't know, which ends up being a lot of what we do, say, I don't know. All right, so just to give you guys, and I can't, this is not yours to have. This is yours to take a look and try and get a sense for, in my perfect world, on my Christmas wish list, like the type of interpretation that you might construct, right? So this isn't a template, it's not something to cut and paste and use. I want you to create your own meaningful thing to go through, but this might be something what an interpretation might look like if someone were to tie these things in together. So for scenario 1, the point estimate of the mean cognitive functioning in the population of older adults taking antioxidant supplements was a mean of 92. What have I done in that first statement that makes me happy? Right? I told you what we're talking about. I told you what the measure is, right? I've oriented you to what we're talking about here. So a 95% confidence interval for these data suggests that values of 84.2, 99.8, reasonable lower and upper bound estimates for the mean cognitive functioning in this population. What's that, Rajiv? What did I do there?
You define the confidence interval in the range of the confidence
Right.
interval.
I provided a meaningful conceptual interpretation of that confidence interval. Not that the confidence interval was this, that's good, but it's giving a practical interpretation of what that confidence interval means. And we say probability of randomly selecting a sample of 25 with an average functioning score of 92 or greater, assuming true population value of 80 is 0.0013. That's, where did I get that, Sam? Where did you get that probability value?
Oh, up there.
Yeah, the Z table right here. I don't know where you're pointing at. The Z table right hanging out. It's just going through, and that's a literal interpretation of your Z score, right? It's the probability of getting something out here. Score falls within the critical region set by alpha 0.05. We reject the null hypotheses. Conclude that antioxidant supplements are associated with statistically reliable increase in cognitive functioning among the adults. Right? Based on the data that we've collected, our population value doesn't fall within our bounds of our confidence interval. Our statistical test gives us a probability estimate that's way out there, right? And so we pull this together and say that we are, based on these data, we're making the conclusion that it looks like supplement use has some type of impact. With scenario 2, this is different, right? This is where we failed to reject. We say supplement use in older adults associated with incremental increase in mean cognitive functioning, right? Relative to scores from the general population, right? So we're saying, yeah, we saw an increase, right? So a jump there. However, confidence interval for this point estimate evidence considerable margin of error, and so we not super precise. With a deviation from population mean, failing to meet benchmarks for a small effect. Don't worry about that. We'll get there later on. Probability of randomly selecting a sample mean cognitive functioning 84 or greater, assuming population value of mean equal 80 is 1.158, 1.59. Score falls outside the critical region, fail to reject the null hypothesis, given insufficient evidence to claim a reliable effect of antioxidant supplements on cognitive functioning. We're not saying that there isn't. We just say that we don't have enough evidence to say that there is. Okay. So again, hopefully your answers will be different, but starting to go through and sort of take a look in the steps going up will force you to start thinking about what's my population, what's the metrics that I'm using, how do I interpret this, what does this have to say about the question at hand, all these types of things that end up being the hard work of statistics, right? Calculating numbers is easy. Calculating numbers. These first couple of assignments that I've given you are the easiest ones we get all semester, because it's basically just counting numbers and finding where they're. But that's easy, right? I can train a pigeon to do that. I don't know if I could. That would be pretty cool. But I have much higher expectations from you all, and so this is the type of thing I want you to do in your own work for this class, is start incorporating this into meaningful conceptual interpretations. Sound good? Cool. All right. Let's do one more example. So here, same type of thing. We're going to go through different memory supplements. I think I stole these from somewhere. It's just all memory supplement stuff. So we've got 36 people, daily herbal supplements for 90 days. What we do is we have them complete a memory test. General population scores normally distributed with mean of 80 and a standard deviation of 18. So here, N36, mean is 80. Standard deviation of the population on this measure is 18. And we got a mean of 84. Okay. What's the first thing we need to do? Calculate our standard error, right? Our standard error here is going to be 18 square root of 36. And give us the standard error. What are we going to do next? Confidence interval, perfect. So we got confidence interval is going to be 84 plus or minus what? Oh, tricked you. Simon says 99% confidence interval. 2.58. Right? Always make sure you're reading the question always make sure that you're capturing the right stuff there. Give this a confidence interval, 76.26, 91.74. Okay, and then what's the last thing we want to do? Calculate our Z statistic. Again, this is going to be 84 over 80 divided by 3, which is our standard error. And give us a value of 1.33. Okay, and if we can look at this in our Z table as associated with probability value, probability Z greater than equal to 1.33 is going to be equal to 0.9. Okay. Well, so I guess I just stepped into steps 2 and 3, or 3 and 4 there. Okay. So before I do this, in a sentence, state the null hypothesis to be tested. Morgan, can you give me the null hypothesis to be tested based on this scenario?
Herbal remedies like ginkgo biloba and ginseng have no effect on
Okay. Technically a correct statement, but probably would lose points on an assignment. Why? Okay, instead of the population, right? Because I want you to be phrasing this in terms of the population, and I want you to tell me what we're talking about, right? So might say something along the lines of standardized memory scores in the population of individuals taking herbal supplements have a mean equal to 80.
Awesome, thank you.
Okay. This is a hard thing to do, right? But it's going to force you to go through, read the question carefully, understand what our outcome measures are, what we're trying to do, right? And wanting you to think about sort of putting this up. I mean, because it's a simple thing. It's a fundamental of all statistics that we're testing, we're running statistics on some hypothetical population. But rarely, if ever, do we actually think about the population, right? At the limitation section, we give a half-assed, like, oh, this might not generalize to all people, right? But rarely think about, like, who specifically, what's the population I'm sampling from? And then who would I like to generalize this to? And is this a reasonable generalization? Is it not a reasonable generalization? Hoping to plant small seeds in your budding scientists' brains to start thinking about some of these things.
So in this example, we're just talking about the general population, right?
What's that?
We're not talking about like a specialized population like we were
No.
before.
I mean, we're talking about the population of individuals taking herbal supplements.
Right, but we're not doing like 65 or over.
Nope, not for this one.
Cool,
Not
I
for
didn't
this
think
one.
so.
Yeah. All right. So that would be a statement of the null hypothesis, and then state the null hypothesis in statistical notation. You say null. Taking people supplements. So say the null hypothesis is going to be the mean, and this is Candace will get you if you're not using population symbols as opposed to sample symbols. So mu of the supplements, right, is equal to what? 80, right? And your alternate hypotheses here, population mean, supplement, not equal 80. That's pretty easy, right? You just want to make sure that you're making these statements in terms of population parameters. And then would want to make an interpretation based on your confidence interval here, right? And what I'm going to ask you to do, make your interpretation of your confidence interval first, right? Once you make your interpretation of the confidence interval, then you can kind of add on the actual null hypothesis test, right? When we get into t-testing, where I'm having you go through and run effect sizes too, I'm going to ask you to first interpret the confidence interval and then interpret the effect size, and then you can throw in a p-value there at the end for everybody wants to see a p-value, but by that point, you've already given all the reasonable stuff that anybody could ever reasonably want to know based on that information there. Okay. Questions about this? Let's stop, grab a break, and we'll jump into the last portion of this when you guys get back. All right, folks. We'll make a push, finish things up. I actually think we're doing pretty good in terms of being on schedule. That usually doesn't happen. We'll be way off schedule by the time we finish up this semester. But finish up with type 1, type 2 error, and then talk about why all this is problematic for very important reasons. Reminder for type 1 error, we make this type of error when we reject the null hypothesis when the null hypothesis is true. We essentially are saying we have an effect, we have a relation in the population when there is actually none in hypothetical real life. This is the type of error that we're always most concerned about. And sometimes that's reasonable, sometimes that's not reasonable, but this is where we fixate our focus, right? We don't want to say that we've got something if there really is nothing to be there, or there's nothing to, no effect to be had. Our alpha level determines our threshold for concluding making this type 1 error. If our alpha level is set at 0.05, reject with the probability of obtaining data, assuming the null hypothesis is less than 5%, right? So a 1 in 20 chance that we just happen to snag a strange sample coming on the margins, right? We're saying that the population of adults taking supplements is actually the same as the cognitive score in the population of adults taking supplements is actually the same as the score of the population of adults who aren't taking supplements. It's just we happen to get a funky mean 1 in 20 times, right? Alpha equal 0.01, reject when the probability of obtaining the data assuming the null less than 1%, 1 in 100 chance, right? So again, just starting to set those boundaries farther and farther out there. So again, graphically, here is our alpha 0.05, plus and minus 1.96. Here is our benchmarks for alpha 0.01, 2.58. 3, our alpha 0.001, 3.29, getting way out there, right? And so we're just making it, what is this essentially doing for our test? It's making it harder or easier to reject the null hypotheses as we increase or we decrease our alpha level. Makes it harder, right? We're saying that the burden of proof for ourselves is getting higher and higher the farther out we set these boundaries, okay? And we might think that this is a good thing, right? If I'm going to say that there's something out there, I should need to demonstrate reasonably that this is a thing, right? But the problem is sometimes we make type 2 errors. And by sometimes, I mean most of the time. Theoretically, always. Our type 2 error is saying that we've rejected the null hypothesis when the null hypothesis is really false. There's an effect out there to be had, we just missed it, right? We're saying that we can't conclude a reliable effect, but there actually is an effect out there to be found. Most commonly associated when our studies have insufficient power. People familiar with the concept of power? You will be, because we'll talk about it. But right now, can someone tell me what we're talking about if we're saying a study has low power or is underpowered? What do you think, Sam? I would take hand movement as offering to answer that question.
Sort of. Like the ability for like a test to find an effect.
Right, right. It's power determines our ability to detect this effect of a given sample, of a given size, right? Type 2 error, we typically don't think about this, right? We're fine in most cases, well, we're not, but from a system standpoint, one would infer we are, about making this type 1 error. But this starts to become more and more problematic if we have a treatment or manipulation that has a small but reliable effect. I've got a heart drug that could save millions of lives. It has a small effect, but it's real and it's there. And if this has a 3% chance of reducing likelihood of fatal heart attack over millions and millions of people, that's a lot of people who aren't having fatal heart attacks. But that's a small effect, right? And it's going to take a pretty powerful study in order to determine that reliably. And so the risk is that people aren't getting this medication that could be helped by it because of this type 2 error that I'm making. Small sample size, poor measurement, outside error, small effects, these are all things that can produce type 2 errors. Yeah.
So if like all things held constant, like if there's like a big effect size, would that directly increase like statistical significance?
You're on the right track, okay? All things being held equal, increase of effect size is going to increase the power of your test. We don't think about increasing statistical significance or decreasing statistical significance in that like something is more significant than something else. Have the same measure, the same test, the same sample size, right? If the effect I'm hunting, right? Hunter safari cap, I'm looking hunting effects, right? The bigger effect is going to be easier to find than the smaller effect, right? I'm going to need less resources to detect that larger effect than I am to detect the smaller effect, right? And so, indirectly, it's going to be easier to claim statistical significance with a larger effect than it is a smaller effect because my test is probably going to have more power, okay? But what we can do, we can't do anything about our effect. Our effect is the effect in the population, right? We can't, unless we systematically go through and start only trying to test large effects, but then you're probably not going to test anything that's too interesting a lot of the time. Small sample size, these are the things that we can do stuff about, right? We can have larger samples. Larger samples are going to decrease our type 2 error. It's going to make it easier. We're going to increase our chances of detecting an effect. We can have good measures, right? If we got poor measures, we got a lot of static in there, right? That's going to reduce the power of our test. These are the types of things that we can do from a system standpoint, from a research standpoint, to make sure that we're keeping our type 2 error as low as possible. Okay?
So what is the outside
what's
error?
that?
So the outside error, what does that mean?
So let's say, Rajiv, you're interested in testing whether or not this system, people using this system is more user-friendly than this system, right? And you're gauging based on overall performance on some task using this system versus this system, right? Seems pretty good, right? You've got everything documented, but no one's actually keeping an eye on people as they're sitting down and working with those systems. And so in addition to one system maybe better, systematically better than the other, you got people on their cell phones, or talking, or listening to music, or getting up and leaving to go to the bathroom and coming back, right? These are all things that are introducing error into your equation that are just going to muck things up, make it harder to test, right? And so if you've got your research assistant there and having people sit down at the same time of day, no distractions, with the same task, controlling all that stuff, it's going to reduce that systematic error. So with our, when we, there's no effect, and we rejected all hypotheses, we're making type 1 error, type 2 error, there's a effect out there, but we failed to reject it, there's a type 2, or a type 2, there's type 1, type 2, as seen here. Typically, our studies are underpowered. What percentage of studies would you think in our field in psychology more broadly are underpowered? well over half. I mean, essentially what you're doing, right? If you have an underpowered study, regardless of whether or not you have evidence or there's actual and effect there to detect, it's kind of like a coin flip, right? Or less, right? Our field is plagued by systematically underpowered studies. A lot of that is because the effects that we're looking to find are quite small. And if we're going to get quite small effects and detect those reliably, we need big samples. We often don't have big samples, and so we have a huge type 2 error problem in our field. But we can also have problems with overpowered studies. When might we be concerned with overpowered studies?
What was the question?
When might we have concerns that our studies might be overpowered? I think so.
If we have like a huge sample size, then any difference between groups would be
Exactly.
statistically significant.
Yeah, right. If we have 1 billion people in our sample, I can posit random associations between anything I like, and it's going to come out because I've just got 1 billion people in my sample, right? And then making large claims about how important this finding is because we've found a statistically reliable effect in a sample of 800 people, right? That can lead to some fairly unwarranted claims, particularly when people don't understand the ins and outs of what's going on, right? So Stephanie finds an effect relation to an X and Y with a sample of 800, and then Alex spends the rest of her career trying to replicate that effect and can't in samples of 100 and is bummed out the whole time, right? Well, we know exactly why Stephanie found an effect and you didn't, right? This is where our effect sizes start to come in. So, okay, fine. We find things that are statistically reliable or not statistically reliable. What's the magnitude of the effect? What's our best estimate of the actual effect in the population? And then that starts to help us layer in a level of interpretation that's going to take us several steps above just identifying p-values that are greater than 0.5 or less than 0.5. Okay. So, a lot of talk about what we do with null hypotheses testing, but if you've been keeping up on the readings, the question that comes up is this a reasonable procedure? Are our inferences warranted based on this system of trying to tease apart true effects for random variation in the data? Null hypothesis significance testing, criticized for decades by very, very prominent, very, very smart people since the 60s and before. We're still doing it, right? And not just criticizing, very, very colorful types of criticisms, fun criticisms that sort of extend out beyond scientific writing into sort of more editorializing things. Described as potent but sterile intellectual rake leaves in his merry path a long strain of ravished maidens with no viable scientific offspring, right? We're just running around, we're doing this. This is a meals analogy. We're not doing anything with it, right? It's just sort of, we think we're doing stuff, but we're not actually doing anything. Cohen, talking about naked emperors, right? Null hypotheses not only failed to support the advance of psychology as science, but seriously impeded it. So not just this has some problems and it's causing some issues, actively impeding our ability to move forward as a field. Despite serving as basis, misuse, interpretation, unwarranted interpretations are the norm, right? People either don't get trained in this stuff, or they get trained and promptly ignore it all and just keep doing what we always do in the field, and this just perpetuates this whole abuse of null hypothesis testing as we move forward. Problems with null hypothesis testing, methodological and conceptual issues that come up with this whole system as a way of learning or understanding the world, understanding psychological phenomena. This is all based on Cohen stuff. That Cohen paper It's assigned in the reading. Hopefully this will help sort of solidify some of this stuff, because it can be a little bit abstract unless you've gone through it 1,000 times like I have. But if we can start to break things down and start thinking about problems with null hypothesis significance testing, problems with the fundamental logic, okay? So our scientific question, what we would like to know is, given these data, what's the probability that the null hypothesis is true, right? Based on the data we've collected, what's the probability of the null hypothesis? That's an interesting and useful question to have from a scientific standpoint. What we actually get with null hypothesis testing is the opposite, right? Given that the null hypothesis is true, assuming the null hypothesis is true, what's the probability of these data? If you think back to this entire lecture, we've been very careful, I've been very careful to talk about this. Say, assuming that the null hypothesis is true, the probability of obtaining a mean of this level or higher, or this level or smaller, is unlikely, right? This is the question that we get with null hypothesis testing. What we'd actually like to get, what would be useful, is say, given these data, what can I infer about the null hypothesis, right? But what we get is, given the null hypothesis, what can I infer about the data? And so this starts to break down when we start to get into probabilities, right? If we say, keep things in terms of true or false. If I say, if the null hypothesis is true, these data cannot occur, right? And the idea, the rationale behind our inference, the inferences we draw, is based on this type of logical structure. If the null hypothesis is true, these data can occur, right? We say these data have occurred, therefore the null hypothesis is not, the null hypothesis is false. This is a perfectly consistent theoretical argument. This is a logical conclusion based on this setup, okay? We're good with this, right? But what we do is we try and pretend that this is what we're doing, but this isn't actually what we're doing. What we're actually doing is we're saying, if the null hypothesis is true, these data are unlikely to occur. So we've gone from cannot to unlikely, right? And what we do is we say these data have occurred, therefore the null hypothesis is unlikely to be true. This is what we do with null hypothesis testing. And this is where we get into trouble. This is fine, right? We say, if the null hypothesis is true, these data can't happen. These data have happened, therefore this is false. As soon as we take this into a probability statement, we run into things like this, right? And so this is, anybody have a background coursework in philosophy, logic, anything like that? Okay. If you do, this is going to be familiar, but you can start to see the problems with this, this basic approach. If a person is American, he or she is unlikely to be a member of Congress. This person is a member of Congress, therefore he or she is unlikely to be American. It seems silly, but this is exactly what we're doing with null hypothesis testing as a whole, right? So from a fundamental logic standpoint, we're not asking the question, null hypothesis testing isn't answering the question we want it to answer, but we pretend that it is, okay? People see where we get into trouble with the logic of this approach. So we've got some, Cohen referring to this as the illusion of attaining improbability. And so we can start to see how the very fundamental inferences that we're drawing from this process start to become nonsensical as soon as we sort of start plugging in actual sort of if-then types of statements. Okay. We also pretend that these probabilities are equal, and they're not. Our scientific question again: what is the probability of the null hypothesis? What's the probability of that the null hypothesis is true given these data? In probability notation, we're saying probability of the null given the data, right? This is what we want to ask. This is a useful question. But what we get with our null hypothesis tests is, what is the probability of these data given that the null hypothesis is true? So in probability function, we've switched this around. We've got, instead of the probability of the null given the data, we're getting the probability of the data given the null. And again, from a logic standpoint, we can start to demonstrate, and Cohen does this quite nicely, showing how these are not interchangeable. These are not the same thing. We can't just flip our probability statement and have the reflexive property here. Probability you speak English if you attend this class versus the probability that you attend this class if you speak English. This next to 100, that next to 0, right, they're not the same thing. So we can't just switch these around and pretend that they're the same thing. What we want to do is we want to reject the null hypotheses because we want to say that the null hypothesis is unlikely given the data that we found. We've observed these things, right? And so therefore the null hypothesis is an unlikely thing. But what ends up happening is, from a mathematical standpoint, this question is actually pretty complex. This is hard to answer. And what we need in order to answer the question that we are interested in, we need to know, and if you've been exposed to any Bayesian types, anybody have been exposed to like Bayes analyses, Bayesian types of stuff? Me neither, right? It's basic understanding of it, but sort of the idea is that in order to determine this, I have to know beforehand, before I run my test, the probability of the null hypotheses to begin with, right? But the problem is we typically don't have an estimate of the probability of the null hypotheses in actual science, right? But what we can start to do is take an example and show like why this problem of non-equivalent probabilities, how this starts to fall apart if we use actual data where we do know prior probability of some event. So in this example, and again this is pulled from Cohen's article, base rate of schizophrenia in the population is 2%. And we run a screening measure that demonstrates 95% accuracy for positive diagnoses, 97% accuracy for negative diagnoses, this is specificity. Right? From a testing standpoint, are we excited about this? If I say your sensitivity is 0.95, your sensitivity is 0.97, do we like this? Oh yeah, we like this. This is fantastic. Right? This is amazing. These are amazing outcomes for a measure, right? And so if we go through and take a look, we say, so HO is our case is normal. So this is someone who doesn't have schizophrenia. Our alternative here, case has a diagnosis. T is our positive or negative test. Our sensitivity and specificity rates can be given here in probability form. Probability of a negative test, given no diagnosis, is 0.97. Probability of a positive test, given a case, is 95%. So we're pretty excited about this, right? And we should be, because this is, in general, pretty good outcomes in terms of a test, right? And so the probability, but what we want to know, what would be nice to know, so this is good. Probability of a positive test given diagnosis is this, probability of a negative test given no diagnosis is this. But what might be interesting to know and relevant to know is the probability of a positive test given that in the absence of a diagnosis, right? We can get this by taking 0.95, subtracting it from 1, right, and getting that. With our null hypothesis test, we would conclude that having a positive test in the absence of no diagnosis would be unlikely. And so if I give, Katie, if I give you a test and it says you have schizophrenia, I'm going to say you have schizophrenia based on this stuff, right? Problem is, this doesn't address the scientific question of interest. What we'd actually like to know, or what would be useful information to know, and this is useful information, right? But it would also be useful to know probability of a diagnosis given our null hypotheses, right? Or excuse me, this is what we're getting, probability of diagnosis given the null. What we'd like to know is probability of no diagnoses given the data, right? So this is what our null hypothesis testing is asking us, right? This is actually what we're getting, okay? So if we're talking about this sensitivity estimate, right? This is giving us the probability that a test result will be positive if the disease is present, right? So the probability of a positive test when the disease is present is 0.95. That's how we would interpret it in sensitivity. We'd say, of the cases of schizophrenia out there, how many did we capture? 95%? Pretty excited about that, right? Sensitivity, going to be probability that a test will result in, test will be negative if the disease is absent, 97%, right? How many of those negatives do we catch? 97%? That's good, right? But from a conceptual standpoint, with our null hypotheses testing, it's saying the likelihood, assuming a negative test, what's the likelihood, or excuse me, assuming no diagnosis, what's the likelihood of negative test? Or assuming a diagnosis, what's the likelihood of a positive test? We're doing pretty good here, right? But what's also interesting to know is the likelihood of a positive test giving a diagnosis, right? And so if we want to calculate the probability of a normal case given a positive test, this actually starts to become more complicated here, okay? And as Cohen puts out, so the probability of a normal case given a positive test, we have to take the probability of a normal case, multiply that by the probability of a positive test given a normal case. There's a positive over the probability of a normal case, multiply that by the probability of a positive test given a normal case, plus the probability of a positive case times the probability of a positive test in a positive case, right? And if we go through and we run this out, right, probability of not having schizophrenia, 98%. Probability of a positive test given a null, given a non-case, taking 0.97, subtract that from 1, right? We get 0.03. Same thing. A non-case probability of having schizophrenia, the probability of a positive test given schizophrenia, 0.95. We actually work this out, and we find that the probability of a normal case given a positive test is actually not low at all. It's actually quite high, right? And as we go through and we start to map this out, we can start to see how this logic starts to fall apart, okay? Where are we calculating the sensitivity and specificity for within this table? Where do we get this 95% probability for probability of having a positive test giving a case of schizophrenia? Alex, can you tell me what row or column we calculated that from here? Yeah, right here, right? What our sensitivity is telling us is that if we take the test positives, the true positives that we got, and we divide it by the total cases of schizophrenia, we do pretty good, right? That's 95%. We also do pretty good if we take all of the normal cases that tested negative and divide that, we're doing pretty good, okay? What have we missed with this that we've actually caught here? Lauren, you have an idea?
I'm trying to think,
Right here, right? If we look at the number of positive tests that are actually positive, that's 20 divided by 50, right? So of everybody who actually tested positive, how many of those people have schizophrenia? We're not doing so good there, right? And for something like this, where diagnosis of schizophrenia may be accompanied by pretty severe medications, like this is a non-trivial issue, right? Basically, we're gonna be medicating a whole lot of people because the test says they have schizophrenia, but they don't have schizophrenia and they don't need to be given heavy medications, right? And so the problem is, and so the point Cohen's trying to make in this article is, this is what null hypothesis is telling us, right? Null hypothesis tests are saying probability of a test given a normal case. Assuming someone is normal, what's the likelihood of a positive test? Pretty low, right? But if we flip this over and actually think about it in terms of what we actually want to know from a scientific standpoint, right? The likelihood of a non-case given a positive test, that's actually quite large, right? And so demonstrating that you can't just flip these probabilities around and thinking that one is equivalent to the other. Now, to be fair, what's the big issue that's coming up with this example? What's throwing this way off? Any ideas? What's that? The low base rate, right? We're trying to, same thing, right? Let's say I'm trying to develop a test for serial killers, right? And I develop a test for serial killers, and I find that my test for serial killers has 99% specificity and 99% sensitivity. Right? How can I easily achieve that? Just make a test that says no one's a serial killer, right? And I'm going to be right 99.9999% of the time, right? Or if I want a very good test that catches serial killers, I'll just put together a test that says everybody's a serial killer, right? And my sensitivity is going to be 100%, right? I'm going to catch everybody who's a serial killer. Problem is I'm going to be labeling lots of people who aren't serial killers as serial killers, and then we're going to run into problems there, right? And so fundamentally, what's going on with our hypothesis test is our hypothesis test is answering a question that we're not asking. And then we're taking the answer to that question and pretending as though it's answering the question that we actually do want to know. Okay? I'm not even going to ask questions because I know there are questions. Anybody have a question they want to ask me right now? Go back through, has anybody tackled this Cohen article yet? Okay. Go through, read Cohen, and then go back through and take a look at this. But wanting you to know both the conceptual and logical issues that are going wrong with hypothesis testing. And so what this does in this example, providing an example of where we start to get way off base using our p-values to start to infer the truth of a null hypothesis based on our sample data. Again, because we like to pretend that we're not asked, but that's what we want to know, right? How likely is the null hypothesis given the data that we've got, right? But what we're actually doing with our hypothesis test is saying how likely are these data assuming the null hypothesis, which is actually the opposite thing and can start to produce very, very different probabilities. Okay. Criticism that's a little bit easier to wrap your head around, maybe conceptually, that doesn't have to do with prior probabilities. Null hypothesis is always false. Okay? Cohen talks about only be true in the bowels of a computer processor running Monte Carlo study, and even a stray electron might make fake. So if the null hypothesis is always false, what's the big deal about rejecting it? Why is the null hypothesis always false? Like, what's the argument behind this? Sam?
There's always some difference.
There's always some difference, right? Nothing is ever going to be identical. It's always going to be the population mean, this mean, the mean in this population, the mean in this population. It's always going to be different to some degree, right? A little bit, right? And so if the null hypothesis is always false, like, why do we get so jazzed about saying that they're different if we know they're always going to be different, right? Tukey, talking about it's foolish to ask, are the effects of A and B different? They're always different to some decimal place, but they're always going to be different. And Thompson, you're getting into this idea of power, right? Significance testing can involve tautological logic, in which tired researchers, having collected data on hundreds of subjects, they conduct a statistical test to evaluate whether there were a lot of subjects, which our researchers already know because they collected the data and they're tired, right? The sample size is the primary driver of our statistical tests. If I haven't reached statistical significance, I will get there if I collect enough people. As my sample size starts to increase to infinity, my power to detect vanishingly small effects increases. And so the argument is, if I've collected a ton of data, and I already know that the null hypothesis is false, why am I doing statistical tests to just tell me that I've collected enough people to tell me that the null hypothesis is false, which theoretically I already know, and it starts to become circular in this way. Okay? And so the problem is the fundamental logic of basing an entire system of knowledge around a procedure to tell us something that we already know before we even start, at least at a technical level. Okay? Cohen talks about, regardless of the specified theory, reject the null hypothesis, expected in the predicted direction half of the time. Okay. So we talked about this a little bit. Why would we expect, regardless of the theory, rejection of the null to be expected in the predicted direction half of the time? Reggie, you want to give this one a shot? So if I know the null hypothesis is always wrong, right? And I'm looking at the difference in A and B, right? And across all questions that could be asked, presumably half the time A is going to be bigger than B, half the time B is going to be bigger than A, right? And so if I just make random predictions on whether or not A is going to be bigger than B or B is going to be bigger than A, half the time I'm going to be right, right? But as I start to make predictions that are in the same direction, if I've got multiple theoretic perspectives on which one, whether A or not is going to be bigger, the likelihood of me just accidentally happening to get a result in the direction that I was expecting starts to become higher than 0.5, right? And so as a consequence, we would expect that incorrect irrelevant theories be supported at least 50% of the time as our power starts to increase. Again, think about my alien commanding height hypotheses, right? My nonsense theory just happens to be predicting things in the same direction as a much more viable theory, right? And so even if I'm just randomly predicting which side is going to be bigger, right? Even if I have no basis in terms of my theory is completely nonsense, at least as my power starts to increase, I'm going to be right half the time anyway, right? Regardless of what crazy theory I specify, right? But as soon as my crazy theory starts to fall in line with other theories that are maybe more plausible, I'm going to get the effect that I want more than 50% of the time, just because we can never, the null hypothesis is never going to be, specifically if we start to increase the precision of our tests, we're never going to have exactly the null hypothesis. And so again, this is a theoretical argument that starts to come into play as our sample sizes get larger and our estimates of precision get better. The Meal paper I'm going to have you read talks a lot about this, right? This paradox within physical sciences, right? As our methods get better, as our measurements get more and more precise, it starts to become harder and harder to find support for our hypotheses, right? Because as I'm getting better and I'm narrowing in on this point estimate, right? And I'm saying that in physics, other hard sciences, my theory says the value will be this, right? And as I get closer and closer and more precise on this, if the value that it should be doesn't capture that, it's starting to get harder and harder and harder to find evidence for my hypotheses. But if our hypotheses are just based on, yeah, it's going to be different, right? Or it's not going to be zero. If theoretically, we always know it's not going to be zero, as we start getting more and more precise and better methodologies, it's almost a certainty that we're going to find it, right? And so the threshold gets weaker as our measurements get better and our powers and our studies get more power with the way we set up our science versus chemistry, physics, things along those. Because I've got Candace is a phenomenal student, right? But I don't think that I would go into Candace's dissertation where Candace says, here's my theory, based on the measure that I've collected, the value that I expect, the mean value for my sample is going to be 53. And if it's not 53, the whole thing's a wash, right? that's an incredibly powerful test of a theory. You're making a very specific point estimate for what that's going to be, right? That's not what we do. What we say is like, well, it'll be different. There'll be a relation between A and B that's not zero, right? And if we know A and B are we already know that A and B aren't related exactly to zero. The correlation's not zero. As soon as my methods get better, my sample size gets larger, my measurements get more precise, it's almost certainly I'm going to find something in the direction that I'm looking for, right? And so this is the gripe about the basic sort of test is ridiculous because we already know that the null hypothesis is going to be false even before we start. Mir refers to this as a credit factor. Everything's related to everything, right? So your theory is sort of nonsense because half the time it is going to be related to be in the direction you expect it to be. Your theory really has nothing to do with any of that stuff. Okay. Questions about why we say the null is always false? Okay. Other criticisms, this idea of dichotomous decisions, right? We're making yes-no decisions based on some largely arbitrary cut point, right? Stole this from a book by Geoff Cumming. Pair of students evaluating efficacy of new intervention for insomnia based on a sample of 44. Lucky, 2012, identified statistically significant advantage of the interaction or the intervention relative to wait list. By contrast, no luck, failed to observe statistically significant effect in a similar sample. Okay. So what would we conclude based on that in a lit review? What do you think, Katie? Yeah. If you're the average person, not Mary Katie Lear.
That maybe what Lucky found was spurious.
Yeah, right. It's inconclusive, right? I don't know. We got one study predicting one thing, got another study predicting the other thing, right? If we're just saying Lucky won, no luck, didn't win, right? Who knows, right? But if we start to go through and take a look at our confidence intervals for both of these, right? 2012 study got a mean difference of 3.6, confidence interval. 2013, smaller sample, right? Yeah, smaller sample, estimate of 2.23, confidence interval here. Confidence interval contains 0, right? And so we say based on this, no difference or no effect is a plausible value within the data that we've collected, right? But if we start to map these out, right? Does this look like we've got two different things going on in these studies? Or not, Angela? What are you saying here? Yeah, a lot of overlap, right? And this one, it catches 0, but right at the end, right? We talked about from that cat's eye approach that Cumming and Finch talk about. We can say, based on the data that we've collected, that 0 is a refuted value, but it's right there at the end, right? It's probably not going to be that different, right? And so, again, if we go through and we take a look and calculate effect sizes for these two studies, here we get an effect size of 0.52, and we're saying that we're getting about a standard deviation difference here. Here we get about 0.3 of a standard deviation difference. They're both in the same direction, right? And they're both suggesting similar types of things, right? But if we just look at this, what we're likely to do is say, one study found a significant result, the other study failed to find a significant result, and so who knows, right? Morgan, what might be a better, more nuanced interpretation of how promising this intervention is? Should we look into this more, or should we scrap it and say, no, there's nothing there?
No, I would look into it because
Right, okay. It's looking like, I mean, a reasonable conclusion might be that we've got only 2 studies. Both of these are small. We've got one study that with data suggesting a reliable effect. The other one failed to reject the null hypotheses, right? But was close and was in the right direction. We've got a small sample, meaning that we have a well-powered study or a not well-powered study. Not well-powered study, which says the type of, our risk of type 2 error is high or low? High, right? If I'm looking at effect sizes, I'm saying, well, we've got what we would call a medium effect here and a small effect here, but they're both working in the same direction. Seems plausible here. I would say that these 2 studies are not opposite of one another. I'd say they're actually kind of looking like they're saying pretty much the same thing. It's just that this one happened to have a little bigger sample and just kind of eked over a little bit to the right than the other one, right? But when all we're doing is just making yes/no decisions based on whether or not something crosses an arbitrary P of 0.05, we start to make these types of errors in inference and thinking that things are much different when they probably are more similar, okay? And so this is why, again, as you're going through, if you find something that has P of 0.055, if you just say nothing there and move on, you probably get a comment that says, are you sure? Talk about this, tell me a little bit about it, right? Because we're kind of right on the edge, right? To treat that as something completely different is probably not taking the level of sophistication that I want you to know. You know, poor Sam came as 0.5 or something like that. Do you still want me to bet? No, that's far enough off. I don't know if that's a marginal case, right? But if it's right there on the edge, right? And the same thing too, right? Just because you sound something at P equal 0.049, it's not the end all be all. Yeah, that's the most reliable effect ever in the universe, right? You just happen to fall on one side or the other on a semi-arbitrary threshold. So last criticism that Cohen talks about is bias against the null. We tend to associate predictions with rejection, with reason, right? Because we don't want to, anytime we predict the null, that's, I don't know what you do with that, right? Because predicting the null just says, I don't know, there might be a difference or there might not, right? We can try and pretend like predicting the null means that there is no effect. And you can't actually do that. And we're never saying that there's no effect. We're just saying that whatever effect may be there is trivially small to be unimportant, right? But what ends up happening is that because we have this heavy premium on rejecting the null, as that being consistent with our theoretical predictions, all the non-significant tests that haven't rejected the null and claims support for the theory don't get published. And so the only tests that do get published, or the only effects that do get published, are those that are very high, and probably what happens then is that we get an inflation of p-values as a product of this publication bias. So if this is the range of an effect, right, that we get, and say our effect is 0, and here's effect that's maybe medium, right? And actually, let's say our effect isn't 0. Let's say our effect is 0.10, right? So there's a, let's give it 2. Okay, we've got a small effect. We've got a small effect in the population. These two, the meaning of these two populations are different, right? But it's just a small effect, right? But what do we know about our power to detect small effects in psychological studies? Is it good or bad? What do you think, Stephanie? Bad? Yeah. What do we need to detect small effects? Large samples and precise measurements, right, which we often don't have. But what ends up happening is, where are we more likely to detect effects when they're larger, right? And so if this is the distribution of effects in all samples that could be detected, right? Which ones are the ones that are likely to get published? The ones near the center or one out towards the tail? Out towards the tail, right? These are the effects that are likely to make it into the literature. And so which effects do you see? These ones, right? And so Lauren, when you're planning your dissertation and you're doing your power analysis and you're saying, all right, what effects do I expect to detect? What are you basing your estimates on? That, right? What's the actual effect in the population? Smaller, right? And so what ends up happening is the studies that do get published, because we're so focused on rejecting the null, what ends up happening is the studies that do make it to publication are probably these studies that are hanging out here on the tail that are a gross overestimate of the actual population effects. Those studies that are probably a better reflection of the true population effects probably didn't reach statistical significance because they didn't have enough people in the sample in order to claim a reliable effect. And so what ends up happening is that we have systematic bias within the literature just based on our publication efforts. So effect sizes in the literature, positive bias, we're overestimating population parameters, right? And so this is frustrating because you say, oh, Raziv's doing a study. He's like, okay, pretty much everybody who's ever done this study and published in this area has found an effect somewhere of 0.4 to 0.7. And so that's what I'm expecting from my study. You're likely to be very disappointed because you may find an effect in the right direction, but maybe it's 0.2, right? And even though you can document an effect of 0.2, your p-value is still 0.4, something like that. And so, right? And you're bummed out, wondering what's going on. Probably bias, or maybe not. Maybe these guys are in the right spot and yours is just way down at the end. What tool do we have available, resource do we have available that starts to give us a sense of whether or not our effects are somewhere in the vicinity of what they should be? These are our meta-analyses, right? The meta-analyses hopefully is capturing not only those studies that found a significant effect, but those studies that failed to find significance, aggregating all those and saying, based on all the studies and data that we could find, this is likely the effect. And looking at things like bile-door problem, like sort of going through and finding tests and studies that have collected these data and not been published and things along those lines, right? And so from the Cohen article, result is that people who do focus on effect sizes end up with substantial positive bias in the estimation. Furthermore, there is irony that sophisticates who use procedures to adjust their alpha error for multiple tests, Bonferroni, so on and so forth, adjusting for non-existent alpha error, thus reducing their power, and if luckily enough to get a significant result, only end up in grossly overestimated population effect size. What is Cohen talking about non-existent alpha error? What is it, Sam?
Oh, I was just talking to myself.
Oh, well, I'm sure it was important. What were we talking to, Seth? We're talking about, what's he talking about non-existent alpha error?
It's talking about like how there were like, publication bias.
Okay, some publication bias. What is our alpha control? Type 1 or type 2 error? Step? Type 1 error, right? Theoretically, can we make type 1 error? Can we say that there's an effect in the population when there's not? No, right? Because there's always an effect in the population. It just might be very small, right? And so what Cohen is saying is we jump through all these hoops to crank down and only report things that meet our Bonferroni corrected test for 8 million tests. And so that stuff that we do find, right, and we say, oh, this is a real thing, ends up being all stuff that's way in the end of the tail of the distribution and not it's just a weird sample, right? We're systematically reporting samples with weird effects because we're only capturing the stuff in the tail, and sometimes you could make the argument that all the efforts that we go through and sort of make things more rigorous and crank down that type 2 error actually systematically inflate the bias that we see in the literature overestimating sort of the true effects that we're actually looking for. Okay? So, make sure, go through, take a look at that Cohen paper, read through that closely. So, in total, what this does is we end up with a group of investigators, a group of professionals that fail to recognize the limitations of our methods. Things our null hypothesis doesn't give us, the extent to which our null hypothesis is true or false. Okay? Your p-value doesn't tell you any of that, right? It doesn't tell you the estimate of magnitude and effect, right? I've got a p-value, p less than 0.0001. I've got a huge effect. Katie, why is that not a reasonable conclusion to make? I say I've got a p less than 0.001, and I say I've found a huge effect. Why is that not a reasonable conclusion? Yeah. So maybe I have a huge effect. I mean, it's possible. What else could happen? Why else might I have a p less than 0.001? I got 1 million people in my sample, right? I've actually got a small effect. I just have 10,000 people in my sample, and so that just forces that p-value to be very, very low, right? So p-values doesn't give us a magnitude effect, doesn't tell us a probability of replicating your study. Now, I'm gonna assign you a paper that talks about the relation of p-values to replication, and it's not there within certain parameters. But what ends up happening, people will look at the p-value and say, oh, p-value of 0.01, I have a 99% likelihood of replicating this study based on the p-value. That's not correct. That's the gross misunderstanding of the whole process and direct support for your proposed theory. Again, we talked about this. Just because you reject the null does not mean, that's not in and of itself support for your theory, right? It just says, if we're being cynical, it just says that you happen to guess the right direction in which that non-existent type 1 error could occur. It just happens to be in the direction that you reported anyway, right? We see rejection of our null hypothesis for a lot of different reasons. Method effects, measurement effects, alternative hypotheses, that's the big one, right? Like, oh, I think it's because of this. Well, it could be because, and probably is because of a lot of different things that just happen to be making predictions in the same direction as my hypothesis. Okay? Things that we can use our null hypothesis test for. Probability of obtaining results as or more extreme than those observed in the data, assuming the null hypothesis is true. Okay? This might not be the question that we want to answer, but it's the question that we're getting the answer to, so we need to be framing our interpretations in terms of what we're actually getting, right? And so our appropriate conclusion, I'm going to hold you guys to this and be looking for it in your write-up. If you reject the null hypotheses, we're saying A is likely greater than B, or A and B are likely positively, negatively related, right? If I fail to reject, basically we're just saying the direction of the actual difference relation between A and B is uncertain, right? Reflecting this idea that from a theoretical perspective, the null hypothesis is never true. One's always bigger than the other. It's just based on these data, we don't have the ability to say which one's bigger than which one, or whether or not these things are positively or negatively correlated. So, why do we keep using this, right? This isn't new stuff. This isn't things that have come out in like the past 6 months that say, oh, our entire science is founded on a sham, right? We've been talking about this forever, right? The problem is one, we need some way to communicate things, right? We need some standardized communication that everybody agrees on. P-values, meaningful common language, right? Across a variety of statistics, right? It doesn't matter if Lauren's doing latent class analyses with regression and so on and so forth, and Angeline's doing chi-squared, right? P-value is the same metric, right? It's a common metric across all sorts of types of statistical procedures. It's an efficient and useful way to communicate information. and it provides a common standard for dichotomous decisions. At the end of the day, we can't just waffle forever, right? We have to choose one side. Either are we saying that there's something there or we're not, right? Now, hopefully we can make those types of interpretations with nuance, right, and take into consideration aspects of the methodology, but at some point we have to say, well, this or that, right? And p-values provide an easy a way to that, in the absence of a better alternative, right? We don't have a better way to go about and do things. Now, people will say we have Bayesian statistics, and in many ways, Bayesian approach has some clear advantages over null hypothesis significant testing. Problem with Bayesian stuff is oftentimes it's requiring information that we don't have access to. And then, to be honest, a lot of it is just training. People don't train. This is the tradition that we've trained in forever and ever. It's the currency of our science, and so it's hard to turn that ship when it's been going in the same direction for 100, 120 years or so. Okay. So, some suggestions offered by Cohen, offered by Howell. Go through, take a look at these. Recommendations from less important people, me. Report your statistical test, degrees of freedom, exact p-values. Don't p less than 0.05, like p less, don't do that. Report your exact p-values. P-value of 0.05 and 0.15, they're not the same thing, right? So that's giving us some information. Report our descriptive statistics. Please report your descriptive statistics. Mean, standard deviations, correlations. But be mindful to report statistics that are relevant to your analysis. We'll get into this in Cumming and Fitch talk about this a little bit in terms of sort of the inference by eye, right? In that assignment I gave you, I was reporting differences in change scores, right? And so if I give you a mean at time 1 and a mean at time 2, you give you confidence intervals around those, but that's a within measures test, it's actually not giving me information about what's relevant to your test. It's because we're looking at the mean of your change scores, right? The mean of difference scores. And so knowing what your statistics are testing and providing information that's relevant to that so that someone else can pick that up and use it. Effect sizes, confidence intervals. I will force you to do this against your will, and I'm comfortable with that. You might not be, but I will be fine with it for this whole semester. So hopefully by the time you get out of here, this starts to become something that you just automatically start thinking about things in terms of interval estimates, effect sizes, stuff. Making sure you're reporting methods that you're using to calculate your effect sizes, confidence intervals, or reporting all your relevant hypotheses tests, not just picking the ones that you like the most. And then being accurate and precise in your interpretation, not saying things that aren't technically true. And Candace and I will beat you up on this. I'll be a circle of it. What about this? This doesn't seem, he's like, well, you know what I mean, right? Well, not you know what I mean, because this is the type of thing that people will, because not everyone knows what you mean. People will take you at face value for better or for worse, right? So wanting to make sure you all are crafting your interpretations precisely in a way that accurately reflects the inferences that you draw from your data. Some stuff on p-values. Report p-values to 3 decimal places. And don't put p equals 0.00. SPSS will tell you that. That's not what SPSS is. It's not, probability isn't exactly 0. It's some vanishing, maybe some vanishingly small probability, but it's not an exact probability of 0. Okay. There we go. Cool.